Today we are going to explore polar coordinates in both the Cartesian plane and the complex plane. We'll take a deeper look at the construction of the complex plane and see how polar coordinates aid us in understanding a well-known theorem. We first look at the Cartesian plane. Let's plot the point A, B. We know from our previous mathematical knowledge that this means the point has a horizontal distance A and a vertical distance B from the origin. Next, we can form a right triangle by labeling the two distances and constructing the hypotenuse. I'm sure that you have heard of a very important theorem called the Pythagorean theorem. It states that when working with right triangles, a squared plus b squared equals c squared. For the purpose of this lesson, we will label our hypotenuse r. Thus, a squared plus b squared equals r squared. When we solve the equation for r, we see that r equals plus or minus the square root of a squared plus b squared. Note that we use the positive value because we are working with distance and magnitude. We can construct a circle with center at the origin through the point AB. Notice that r is the radius of this circle. We will want to keep this in mind for later in the lesson. Also note that we have an angle formed between the x-axis and our r segment. We label this angle theta. So what kind of relationship do we see? I'm assuming from previous knowledge that you know the acronym SOHCAHTOA, where sine equals the opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent of theta equals the opposite side over the adjacent side. In our case, cosine of theta equals a divided by r, and sine of theta equals b divided by r. When we multiply each of the equations by r on both sides, we get that a equals r cosine theta, b equals r sine theta. Also, we know the tangent of theta equals b divided by a. So now the point AB in polar coordinates becomes r cosine theta, r sine theta, where r is the radius of the circle and theta is the angle between the radius and the x-axis. Now we are going to transition to the complex plane, but we need to have some background information. Remember, when we were working in the Cartesian plane, we had an input A and an output B. That's how we got the ordered pair A, B. Things work a little differently in the complex plane. First off, the points in the complex plane have the form z equals a plus bi, where we're adding the real component to the imaginary component. So what does this look like? Let's take a little detour for a second in order to understand where this imaginary axis comes from. We start with a real horizontal line. What happens when we multiply a value, let's say 1, by -1? It flips to give us -1, like this. So multiplying by -1 is rotating our entire real line by 180 degrees. We know that by definition, I equals the square root of -1. So what does I squared equal? I squared equals I times I, which equals the square root of -1 times the square root of -1, which results in -1. So multiplying by I squared gives us a 180 degree rotation because I squared equals -1. So what happens if we just want to multiply by I? In other words, where would half of this rotation be? -90 degrees. Thus, 1 times I lies above the real axis. We can construct a perpendicular line through the point 1 times I and the real line to form the imaginary axis. Let's do an example. Say we want to plot the point 1 plus 3i. The real part is 1, so we start at the origin and move 1 unit to the right. Then we want to add 3i. Since 3 is real, we can shift 3 units to the right on the real line. But note, as we stated above, multiplying by I will rotate the point 90 degrees. So this point is 1 plus 3i. Also, we can make a connection. Let's say we want to plot the point 1, 3 on the Cartesian plane. We can see that these 2 points are in the same place. However, one is an ordered pair with an input and output, and the other is a single value. As you have seen, our points take the form z equals a plus bi shown here. Plugging in our polar coordinates for a and b that we found earlier, we can see that z equals a plus bi is now z equals r times cosine of theta plus r times I sine of theta. When we use the reverse of this distributive property, we can factor out an r in order to get z equals r times the cosine of theta plus I times the sine of theta. Now the point A, B in complex coordinates becomes r times cosine of theta plus I times sine of theta. Since we saw that z is a single value, this means we can multiply 2 vectors in the complex plane together, which is something we can't do in the Cartesian plane. Let's try multiplying z by itself. So z times z equals a plus bi times a plus bi, which equals a squared plus abi plus abi plus bi squared. We saw earlier that I squared equals -1. So now we have that z times z equals a squared plus 2abi minus b squared. We found that in polar coordinates, z equals r times cosine theta plus I sine theta. What do you think would happen if we squared both sides in polar form? Use your knowledge about squaring equations to see what you find. A helpful hint is to note the double angle formulas, which state that the cosine of 2 theta equals cosine squared of theta minus sine squared theta, and sine of 2 theta equals 2 times sine theta times cosine theta. You have most likely either seen or used these theorems in previous math classes. Pause the video in order to work. Foiling, rearranging our terms, and using the double angle formulas, we get that z squared equals r squared times cosine of 2 theta plus I times the sine of 2 theta. What do you notice? What do you think would happen if we raised both sides of the equation to the 3rd, 4th, 10th power? What about to the nth power? Pause the video to discuss with a partner or your class. What did you see? Did you notice that the exponent value matches the scalar on theta? We can generalize this process in order to get z to the n equals r to the n times cosine of n theta plus I times the sine of n theta. This formula is known as De Moivre's theorem.
We have one last connection to make. So we looked at polar coordinates in the complex plane. We had z equals r cosine theta plus I sine theta. So r is the radius of the circle and theta is the angle between r and the real axis. We saw that with De Moivre's theorem that when we're changing the exponent of z, this is causing our radius to change directly and also affecting our theta. However, when we look at the unit circle with radius 1, we simply are rotating around the circle because the radius is not changing, since 1 to any power is simply just 1. This concludes our discussion of the complex plane and polar coordinates. Hope you enjoyed.